Hi, student. Back to Cook RT again. What I'm going to do today is I'm going to talk about a basic digital logic design by using spice and then in the term of decoder and coder circuits. As I upload on YouTube before, I'll talk about the basic digital logic in general. But today we can move forward and actually just like use the basic idea of what we have studied and then take a look at decoder and coder circuits, and also in addition with PSpice to get a better pictures. We'll show you also on the PSpice. Let's get started with decoder. When you're talking about decoder, for example, in front of you here, we're talking about a 3 to 8 line decoder. That means you have a 3 input, A, B, C, or a 3 bits input, and then what you get is you have 8 output. This means from Y0 to Y7, and you know that for 3 bit input you are going to have all the combination to be to the cube or equal to 8. So that's why you end up with the output to be Y0 and to Y7. Next is that what I have here is the truth table. I list the input ABC as the I have with the all combinations. Example, you have A um, have like 0, 0, 0, 0, and then 1, 1, 1, 1, and then that's all related to your output as shown here. That's mean when you have an input to be 0, 0, it's gonna correspond to your output, at this point here. And what I have here is that you can imagine that if you want the logic of the output to be 1, you can just already set up Y0 to be 1, and then for number 2 or input become a 0, 0, 1, that's going to correspond to the output Y1 to be 1 only, and the rest going to be 0. So the rest is going to be the same thing. Okay. Now that's why we call decoder. When you have 3 input, you can relate each input with your output as shown on the truth table. And for example here, when you set up Y0 here, and if you're thinking about the min term, right, that means your input have to be A bar and with the B bar and with C bar. So we end up with Y0 equal to ABC. For let's say Y5, you have input is the 101, and that's going to correspond to Y5 as the output, which is 1. So what happened is that when you're talking about a min term, you're gonna have the you can write Y4 in the term of ABC as the A, and then end with the B bar or B complement, and then there's C. So that's why I have A, B complement, and C. This is my Y5. Okay, so that's when you're talking about a min term. Next, um, as I have here, you can also draw the digital circuit. Corresponds to each output, mean Y0, Y6, Y7. And this type of decoder, we're going to call it as the we call it the 3 bits and 8 to 8 line decoder. And as I show here, when you have 3 to 8 line decoder, you have 3 inputs, so you end up with 8 outputs. And then now you're probably wondering, if I have a if I have 4 inputs or 4 bits to 10 lines decoder, what does this mean? This means you're going to have like input 4 bits, so that's you going to give you the output 16, but sometimes we use only 10 line only, so you ignore the rest. So basically you can say that for n the power n line decoder is going to generate um, to to the n output, right? That's what you can have as the output. So this is general idea about decoder. Next, you're going to see I will show you some example as the application. When you're talking about a 7-segment LED display here, okay, as you know that you have LED in the arrangement just like in the figure here. Start from A, B, C, D, E, F, and G. That's how you uh, create a number by using a digital logic system. And each, like LED is represented by a LED diode or light diode. Now when you take a look at the truth table, when you have like 4 inputs, okay, and you can write all the combination just like this one here. So if you have 4 inputs, you're going to have 4 to the power 2 to the 2 to the power 4, and that's give you a 16. So I break this up to be 8 for 0 for the input, and the rest is going to be 8 of 1 logic 1. Okay, let's move this up a little bit. Here we go. So if you want to create a number here, if you have input A, B, C, D, A, B, C, D, and I start with number 0, this is give you 1, right? This is the least digit number. This is the most digit number. And then for 8, you know that it's going to have the logic to be 1, and the rest have logic 0. That's give you the number of 8. And you want this one to show up, on the 7 segment LED. Let's take a look. For example, you want to create the number of 0, so you have something look like this, so you ignore G, right? Now which one is going to turn on or give you to be the logic 1? So almost all of them going to give you the logic 1 except G, so that's why you put 0 as G here. Let's give you number 0. And then now you take a look at the number 4. Let's take a look at this one. This is your 4, correct? So what you need to be on is the output as the F, G, B, and C, right? So this is your number 4. Take a look. So you need B to be 1. That's why I put 1 here. That's why C to be 1. That's why I put 1 here. And then you need F to be 1, and you need G to be 1. That's give you number 4, and the rest is going to have logic to be 0. Okay, so you probably get some basic idea already. And then from this here, you can make your digital circuit. So that's why I give you example of for example, if you want the output A, you look at this one, and you start doing the kernel map. So let's say I have 0, 0 here. My 0 is easier, right? Because you only have 2 0, and also this one here. So for DCBA, with the logic 0 0 0 1, I give A to be 0. Now take a look at this one. I have output A, right? 0 0 0 1. This is your 0 0 and then 1. And this is also B becomes 0. So you pick up this one here, put 0. And also another 0. What's that for the output A? You have 0 1 0 0. This is 0 1 0 0. So that's why I put 0 right here, and the rest just simply put 1. Now you have to simplify your counter map. So what I have, I draw, like the red rectangle. So I have 1 2 3 4 terms. So for this term, you need to write down the input. Since you take a look from the top to the bottom here, all D and C change. So you not take D and C as the input here. For from the left to the right, it has only one column. So I'm sorry, from the left to the right, you have only A. Oh, sorry, only B doesn't change because it still have the logic to be 1, but for A is change the logic from 1 to be 0. So that's why you pick up B only to be your input as the first term. Okay, now move on to another step. Let's take a look at this one. You take a look from the top to the bottom here. Now from the top to the bottom here, you can see that what doesn't change is C, correct? Because C still become a 1, but D has changed from 0 to be 1, so that's why you pick up C here. Now from the left to the right, you can see that B and A, B had changed from 0 to be 1, and A is still the same, be 1 and 1, so that's why you pick up A. That's why you have this term to be your C and with A input. Next, for this the rectangle, you move from the top to the bottom. You can see that D doesn't change, but C changed, so you keep D here. Now from the left to the right, you have B still becomes 0, right? But A had changed from 0 to be 1, so that's why you keep B, but B has to be B bar because B is 0 here. And next, you take a look at this term here, rectangular, that you can take also take into account of this part. So as you can see, you move from the top to the bottom. You need to make sure that you have this guy here and this guy is here. You can see C doesn't change, but C is 0, so that's why you put a C complement or C bar here. And then when you, because this is have only one column, so BA still be the same, it's never changed, so that's why you put B bar or B complement and A complement. They are AND together, so that's why you have full terms, right? 1 here 2, 3, and 4. This guy. Okay, so this is how you design your output for output A. And then you also can go to your PSpice to draw the circuit for output A. This is how it works. Next, um, ROM or read-only memories. That's the basic idea. You have three input lines, the input A, B, and Z, and then you have four output. That's we call four output lines. And this type of ROM we call 8 words 4 bits. 4 bits come from your output. That's have 4 bits. And your input here, 8 words. Oops, sorry. I take it back. 8 words mean because you have 3 input lines, so you have all combination to be to the power cube. So that's give you 8, and that's why it's give you total combination to be x, and you have all M0 to M7, so that's what we call our 8 words. And output you need at least 4, right? You have 4 bits. And then what we're going to do next is we are going to get in more detail to the ROM. As you can see, your input here, ABC, you have all combination for A00001111, and I put this one line, and M is the midterm, so I have M0 to M7. Now, or if I leave this output as the F0 to F3, how can I come up with this number or the logic like this? Well, now you take a look at the okay. Now take a look together carefully. I come up with this one. You can see that y f0 to be f1 and f2 f3 to be 10 10, and this one y is have to be 10 10 10. Okay, so keep that question in your mind. Well, what I did is that your output to be anything that you want. Okay, because you want output to be as you want you design. So this is nothing to do with your input here. It just I want M0 corresponds to this line, and I want M1 to correspond to this line, or number 2 I want it correspond to this one. I just want to show you, that's all. Now you take a look at the ROM. Okay, let's go to the diagram here. I have 3 input A, B, C, so I call it 3 to 8 decoder, because it's going to have 8 lines, right? And this one you have to the cube, or to the third, and that's give you 8. That's why you have output as the 8 output, or I will say is 8 word lines. And this is my output F0 to F3. Now let's get started. If I want my output to be like this, for example M0, right? I want my F0, F1, F2, F3 to be 10 10, and then M5, I want my output to be 0, 0, 0, 0, 1. What you have to do is that you take a look at, let's start with F0 here. As you can see, you look from the top to the bottom here. Now we're going to take a look at the min term, right? As you know, when you're talking about a min term, you are use the AND input, right? A has to be AND with B and to have to AND with C. And for each term, you just OR them together. This means that you have to OR M1 to M4. But at this point, we interest in F0, so you take a look at the min term. What does this mean, min term? Min term is the term that gives your output to be 1. So I have right here, right here. So F0 is come from M0. You take a look at the when F0 become 1, your min term is this, in the term of input A, B, C. So you have what? A, B, you add them together. And when you want output to be 1, you cannot leave it just like this. You need to put a complement, or I put a bar, B complement and C complement. So they all change, this one from logic 0 to be 1. So that's why you end up F0 to be 1. The same thing as M1. You also have F0 as the output to be 1. You need to add these guys together. So you have what? A, B, and C, right? And now you need to consider A has to be a complement to change logic 0 to be 1. Also B, you need B complement. But C is already have logic 1, so you just leave it like that. Okay, hopefully you understand. Alright, take one more example here. For M6, you want F0 to be 1, so your min term have to be what? A, B, C. A is already 1, B is already 1, but C is 0, so you need to put the complement or C bar here. Okay. Now take a look the way you connect the circuit together when you're talking about F0 and M0 here. You look at the diagram. So from M0, you need A bar, B bar, C bar. Okay, they all complement. So this is your F0. Now you take a look at the first word or the first line or 0 line. Let's say that M0. You need A complement, B complement, and C complement. This is your A, B, C. And your M0 is already represent right here. M4 is also be here. So what you need to do is you need to connect M0 to your F0. Okay, this is your F0 line. And then this one is just like diode. You connect this one to the ground, right? And this one, if it's the status logic become 1, so this one is higher than this one, so your diode is turned on. If it's become a LED, that means your LED is on, because for the diode you need to bias on this side to be positive, or the voltage has to be higher on the inside, right? This is P side. And also F0 have M1, so you need to connect M1 to F0, and you need to connect M4 to F0, and then M6 to F0. So that's why you have M0 and then M1, 0, 1, 4, and 6. Zero, 1, 4, and 6. That's why I have output for F0 to be like this. And you do the same thing, right? If you take a look at the, let's say F3. When you're talking about a min-term, you need to connect M0, right? Just take a look at the logic 1. So you have 2, 3, 5, and 2, 7. 2, 3, 5, 6, 7. Oh, sorry. I just leave it like this. So you have what? You need to connect 1, 2, and then 5, and then 6, and then 7 to your F3 to get your output F3 as the according to the truth table here. Okay, so this is how our read-only memories or ROM works. And right now here I have sorry, I can write it out. This is for F0, so I have a need OR gate, right? Because these are midterm 0 1 4 6 0 line, 1 line, 4th line, 6th line. And for F0, that's why I have a midterm here as the 0 1 4 and 6 0 1 4 and 6. What you need to work out, you have to write down your M0 here. It's in the term of A complement, B complement, and C complement. They are all AND together. For M1, you have A complement, B complement, and C. 4, you have A, B complement, C complement, and 6, you have A, B, and C complement. And you can simplify, this one by using Boolean algebra, whatever, you go to end up with, your F0 in the term of input ABC, just like this: A complement and with B complement, and then OR with A and with C complement. And for F1, you're going to do the same thing. You have a midterm, it's the M2 line, M3 line, M4 line, M6 lines, and M7 line. And after I simplify all equations together, I end up with your F1 in the term of input as B or with A and with C complement. And you check, by yourself for the rest, for F2 and for F3. Now let's move to the next page. What I'm going to do next, I'm going to do more advanced problem of digital logic design. You're talking about coders and similar sequential networks. What does it mean, sequential networks? Sequential networks mean they all input. For example, if you input the clock to your system here, or your flip-flop, going to receive the clock at the same time. Or is mean that when you have the clock show up here at C, you're going to have the clock signal show up at B at the same time as C, and as well as the clock show up at the A flip-flop. So that's what we call sequential networks. Now what I'm going to do is that when you're talking about the counters, when you input the clock into your circuit, you start from 0. The next clock is coming in. You want it count, number of clock to be 1, and the next number of clock increase to be 2, and then 3, and 4, and so on. And when you finish, clock number 7 is come back to 0 again and start, the cycle the same, become 2, 3, 4, 5. Now how do you design the counter circuit like this? Well, you take a look at this one. I have my truth table for input ABC, and I put a number here. So you start with for the total combination is going to be 8, right? So that's why I have the truth table and logic A to be like this, logic B to be like this, and also logic C to be like this. So what I have is I have another output. Okay, I will show you soon. Now what you need to consider is that if you have 3 flip-flops, start from C, B, and A. You have input TC, you have input TB, and you have input TA to the flip-flop. Now, if you send the clock from the left to the right at C, when the clock coming in, it's gonna change the logic of C, right? And then after that, for input TB, seems that C have to receive the clock first, and B also have received the clock at the same time. But if no clock coming in, you have no output here. So what I try to explain is that you also cannot simply input the clock to the flip-flop B, and you cannot simply input the clock to the flip-flop A. What you need to do is that you need to think about, if you have no let's say logic 1 coming here. Sorry, you already have clock here, but you also need to consider, the logic, from C. If your logic C is 0, it means it's no clock coming in C. You need C to be logic 1. That means the clock already input to the C flip-flop. So you're going to have TB input when your C become 1 with the clock signal is coming in. You can count. So your TB, that's why I put the AND gate here together. It's might a bit confused here, but try to explain by yourself. Now you understand this part. For input TA, you know exactly that you require input clock, and you also require input the output from B, and you also need the output from C. So you end up with a 3-input AND gate for TA. It has to work this way. It means that if C doesn't change, you cannot, start counting the number of clock. C has to change. That means it has to be 1. Okay, to this one I have your TA input. You need a 3-input AND gate. One is from C output, one is from B output, and one from clock. Well, if you understand this part, let's move to the truth table. Okay, this is I also put when the clock coming in, you simply input the clock to TC is going to be just like the clock, but for your TB to input to B flip-flop, you need output from C. If C doesn't change, it means you don't have TB. The same concept for TA. If TB doesn't change, you don't have TA. Also, if C doesn't change, you don't have to do anything. So all from output from C, output from B has to change or become logic 1. When the clock coming in, that means you have logic 1, you can have TA. If one of these becomes 0, you're going to have output to be 0. It means you don't have to do anything with TA. Okay, so to get better picture, let's go to see the truth table. And if you understand the basic idea, you see this is the present state, number 0, 1, 2, 3, 4, 5, 6, 7. This is just normal or truth table. For 3 input ABC, you have 0, 0, 0, 0, 1, 1, 1, 1 for A, right? Now for the next stage, I put the positive sign here. So that's mean for the clock number 1 is coming in, ABC input used to be a 0 0 0. Now you have to change the state, to next stage. So you need to move this one up to show up as the next state for input A, B, and C. And then for this one, you need to move the number 2 state to number 1 of the next stage. That's what I mean. This is number 1. Now for flip-flop input, we're talking about TA, you're talking about TB, and you're talking about TC. You might confuse, but let's see how I can come up with this logic. For example, why I have number 1 here to be TA, TB, TC becomes 0, 0, and 1. Okay. If you compare between the present state and the next stage, if C change, it gives you input TC to be 1. But if C doesn't change, let's see where C doesn't change, you don't have it. So TC always be logic 1, right? Now let's consider TB. It's work the same thing, If the present state of B doesn't change, your TB logic have to be 0. But whenever the logic of B change from 0 to 1 or 1 to 0, you can put the logic TB to be 1. Now let's take a look at the first one here. Number 0. You have B 0 and it still becomes 0, so that's why you put 0 here. And then for number 1, B present state of B to be 0 and the next state is 1, so B has changed the state, so that's why you put 1 here. Same thing as number 4 here. You take a look at present state of B 0 and the next state is still 0, so that's why you put 0 here. Now for the number 7, you have the present state of B is 1, the next state is 0, so that's why you have 1 here. So it's work the same as the TA. Take a look at TA. Number 0, present state is 0, next state is 0, so your TA is still becomes 0. Now for let's say number 3, you have present state of A logic 0 and the next state the logic of A is 1, so A has changed the logic, so that's why you put 1 here. Okay, so that's how you come up with TA, TB, and TC. That's why I explained here, whenever C and C plus are different, the flip-flop C must change, so your TC has to be equal to 1. It changed because when the clock is coming in, when you have no clock coming in, it means your C doesn't change the state, right? And that's why I also put same as B and B plus, as well as A and A plus, or present state and the next stage. When you already have the truth table right here, you can do the kind of map to find TA, TB, and TC. Then you take a look at TA first. You have your TA with the logic 1 from the line number 3 right here, and you're interested in your input ABC, right? So it's come from 0 1 1, and also our TA logic to be 1 is come from the input ABC is 1 1 1. Okay, so let's do this. 0 1 1 and 1 1 1. For TA, you have 0 1 1. This is 0 1 1, right? C become 1 when A is 0, B is 0. Oh, sorry, 1. And also our ABC is 1 1 1. You have A and B1 here, B1, and then you're looking for C's 1, so that's why I put 1 here. So the rest is you put 0. So when you do the counter map, you can write TA in terms of input ABC, as shown here, B, C, P. P simply just clock. You also need clock. You look at the top from to the bottom. This means you look at this part, right? B doesn't change, but A change, so you keep B. From the top, left to the right, because this is on the only one column, so C here still stay the same, and simply just C. So that's why you just put C here. And now for TB, you look at the truth table, you can do the counter map. This is your TC. Let's say TB first, right? You have 0, 1, 0, 1, 0, 1, 0, 1. You have 4 ones. So I have TB here. And then you can write TB in the term of input ABC, by taking a look at from the top to the bottom here. A and B, they all change, so you ignore A and B. But this one has only one column, and C here has the logic 1, so you simply put C here, and also end with clock. Now our TC, as you can see, TC has the logic 1 only, so it's easy to do the counter map here. That's why you have nothing to do with A, B, and C. Simply you just put the clock here. So this is your input TC here in the term of the input A, B, and C. Now okay, this is just the idea how to design your counter. And then I'm not sure if I have before I explain to JK flip-flop and design the circuit by using the PSpice here, and I also have complete circuit for counter. I will explain to you in the next YouTube. Okay, thank you.